Okay, these notes are on binary searching. So the purpose of a binary search is to find an element in one of the cells of an ordered list. So the most intuitive way to search an ordered list is just like you would any arbitrary list, which is you start at 0 and then you go to the next cell and then you keep going at every cell until you get to the end of the list. But this quickly becomes very computationally expensive the longer the list or array is. So if we have a list that is ordered, because of there are some assumptions that we can make about an ordered list, and we can make these assumptions confidently that we can't make about a regular list. So if I say pick a random cell and I check the value in that cell, then if the value is greater than the one I am looking for, then I know that none of the cells that have a higher index than the guessed cell can possibly contain my value because the list is in order. So if I pick cell 3 here and I'm looking for a value 2 and the value in cell 3 is 4, I know that cell 4 and 5, which contain values 5 and 6, certainly do not contain the value 2. So I'm better off looking to all the cells to the left of the initial cell that I guessed. And that is the principle of binary searching. You want to eliminate the total guessed space from your array. So you're basically breaking it into subarrays, and these subarrays are each smaller than the last. So to demonstrate this, we're going to create an array with a length of 9. What is the best guess? Let's say we're looking for the value 7, or we'll do 4. What is the best guess for what cell is would be the best guess for what contains the value 4? Well, initially on the first guess, knowing that the value you want is 4 doesn't help us at all, because this array could conceivably contain any value of numbers. There is no better cell to guess. So the optimal way to play this game, where we're trying to eliminate the largest number of cells possible, is to just pick the middle cell initially as a value to check, because it will guaranteed to eliminate half of the cells. So if we check the middle cell, in this case, let's get 9 total cells. If we check the middle cell, in this case, let's say it's 5, we know everything to the left of it certainly doesn't contain 4 because it's ordered. And then we're left with basically 2 arrays. One that we know doesn't contain our value, and one that may contain our value. And we use the same strategy, which is we want to eliminate half of the remaining cells. So we're going to split it in half, and the closest we can get to half is the first the cell with indice 1, which say contains the value 2. And now we know that the cell to the left of 2 definitely doesn't contain the value of 4. All right, and then somewhat arbitrarily, we pick the first cell in our subarray here, or the better put, the left cell in our subarray, which say is also a 2, and now our last remaining cell may or may not contain 4, and in this case it contains 4. So we didn't have to check, in this case, we didn't have to check every cell. In fact, we guaranteed that 4 wasn't in the first cell with indice 0, and it also wasn't in this cell with indice 6 or 7 or 8. Because we knew some prior knowledge about ordered arrays, we were able to reduce the number of total comparisons, which saves computational time. So to program this, let's say we want a function that runs a binary search, and it takes a value in an array. The first thing we want to do is get the scope of our array and create the first subarray, which initially, because we don't know anything about the array other than it's ordered, will just be the entire array. So the starting index will be 0, and the ending index will be the array's length minus 1, because arrays start at 0. All right, and then we want to run some process through the array to check for our value. And this process is what was demonstrated above, up here. We know that we're done playing the game, so to speak, where we split the array and check the value of the middle cell, when either we found the value, which we will get to in the middle of the loop, or the value of the end index is less than the start index. Because when they're equal, we're just checking one last cell. And when the end index is moved to the left of the start index, then we know we need to leave the loop. We've not found the value for sure. And if we haven't found the value, we need to return null, or an equivalent value that indicates that the value in our array, our ordered array, was not in the, oh sorry, our desired value was not in our ordered array. So that's when our start, so we leave the while loop when our start is, or when our end is less than or equal to our start. Oh sorry, we stay in our loop as long as our start is greater than or equal to our end, or less than or equal to our end. Sorry for the confusion. Okay. All right. So now we need to get the middle value, or the middle indice, which is just the average of our of the scope of our subarray, which is the start plus the end divided by 2. And you can think of that as the points between 2 points is the average of those 2 points. All right. And then our cell value is equal to our array at indice middle. which will be used to which we will compare to our value that we pass to the function itself. So, and then we think about the conditions of our check, whether or not our value is equal to the cell value, or our past function value is equal to the cell value, is going to determine whether we send back the indice of the array that contains our desired value, or whether we run the binary search again with a subarray. So let's do the two conditions for splitting our initial array up into two subarrays. So the first one would be if the cell value is less than our start or our past value. And in this case, we would know everything to the left of our cell value, or all of the cells to the left of our middle cell, certainly does not contain our value. So we would move our starting indice to the middle, which we also know doesn't contain our value, seeing as how it is the cell value is less than our value. It guarantees that the cell value is not equal to our value, which means we know that we don't have to check the middle again, which means we can just increment the middle by 1 as a point to move our start value. All right, and then the other condition would be our cell value is greater than our desired value, in which case we would move the end to the middle value minus 1. So we're basically moving the right indice all the way to the cell just left of our middle cell. All right, and then the last condition is if they're equal. If our desired value and the value in the middle cell are equal, we just return the indice of our middle value, which is the middle index that we created after averaging the 2 points up here. All right. And if none of those conditions are met, actually one of them has to be met. But if we don't break from the entire function on this line, by the time this condition statement has finished, then we will just go to the top of the loop and it will start completely over, which is basically just continually chopping our array into smaller and smaller pieces. That is what that contributes to. And if we get to the end, this was already explained, if we break from the while loop here, based on its starting condition of start is less than or equal to end, then we know that it just our cell value is just not in the ordered array, and then we return the correct value that would indicate that. And that is the binary array explained, and also how to implement it in pseudocode.